means when sigma was known. Now we're going to look when sigma is unknown. When sigma is unknown. When sigma is unknown, you're going to use the t distribution, okay? And so you're going to use the t distribution. I think I have that wrong there. It's going to be the t distribution, okay? So, and because that's what we use whenever sigma is unknown, because we don't know the population standard deviation. So the drug 6-MP is used to treat leukemia. The following is remission times for random sample 21 patients. The sample mean 17.1 with a sample standard deviation of 10.0. So we don't know the population standard deviation. The X be a random variable representing the remission time for all patients. Assume it's mound-shaped and symmetric. So mound-shaped and symmetric means that it's approximately normally distributed. The previously used drug treatment had a mean remission time of 12.5. Do the data indicate the mean remission time using this one's different in either way? Okay, use the alpha 0.01. So let's start with our null hypothesis. Now the question is, it's mu because it's one sample means, equals, always equals for Ho. Which mean are we looking for our hypothesis? Which one's kind of the claim we're going against? The sample mean or this right here, this 12.5? 12.5, right? This is the mean we're trying to do a test against. So it's going to be mu equals 12.5. H of 1, these two are the same. Now this could be different. It's either less than, greater than, or not equal to. What am I trying to test here? What am I trying to test? Different. So different means not equal to. Okay? So different means not equal to. So there's my hypothesis there. Now I got to figure out what distribution to use. Okay, well they said it's mound-shaped and symmetric. So that means normality is satisfied. So you could say it's approximately normal. It's approximately normal. So that's why they said that. So you could say the normality assumption is satisfied. And the key is sigma is unknown this time. So if sigma is unknown, if sigma is known, we use Z. If sigma is unknown, what do we use? T. So you can go to stat, test. We're doing a test because we're doing a hypothesis test, and you're going to do t-test here. Okay, stat, test, t-test. Okay, stat, test, t-test. Stat, test, t-test. Option 2. You've got stat mu naught. You don't have to write all this down. Mu naught is the null hypothesized mean, 12.5. X bar is the sample mean 17.1. S of X is the sample standard deviation, that's 10.0. And N is the number in our sample size, and I've got 21 patients, so it'll be 21. And then in this case, it's not equal to. It's not equal to. I'm going to do the draw function again. I like the draw one. Okay. Notice on this one that it's different, so it's not equal to. So it's a two-tailed test because both tails are shaded. So you've got a two-tailed. I'm just going to do a rough sketch. So it's kind of like this. Now, this time the test statistic is T. It's 2.11, or yeah, 2.11. And the p-value is 0.0478. Remember, alpha is 0.01 here. Okay. Now we're ready to make our conclusion. How does the p-value compare to alpha? How's it compared to alpha? Is it greater than 0.01 or less than 0.01? Greater than, right? When p is low, reject the Ho. Okay, now, is p lower than alpha? No, so we fail to reject Ho once again. And this means not statistically significant. So basically what we've shown here is that the gap between the mean was 17.1 and the claim was 12.5. The gap between these two is not significantly different. The gap between the sample mean and the hypothesized mean is not, this gap is not significant. Okay. So we have, you could say not sufficient or insufficient evidence to say that the mean remission time, I'm just copying this down, that the mean remission time using the drug 6-MP is different from 12.5 weeks. And you just get to match it on there, on your mission time using the drug 6-MP is different from 12.5 weeks. Okay, so if you want to, that's all you have to know. I'll do by hand again if you want. Okay, so how you do this by hand. This time we're doing a t-statistic. It's equal to the sample mean minus the hypothesized mean over the sample standard deviation divided by the square root of n. This is how I get my t-statistic. So I'm going to go ahead and enter this in here. As I said, this is kind of optional. 12.5 divided by 10 divided by the square root of n, 21. So real world, you'll have technology for this. I'll move this out of the way here in just a moment. So 17.1 minus 12.5 divided by 10 divided by the square root of 21. To get, that's where you get the 2.11 from. I'm going to go with 3 spots this time. Okay. Now, this is a little different now. As I said, you don't have to know this, but how do I get the area? Well, it's a two-tailed test. So you have a high end T of 2.108, and then you have a low end of negative 2.108. Okay, and then for the T, you use degrees of freedom. Degrees of freedom is n minus 1. So degrees of freedom is 20. So you could use there's a thing in your calculator called TCDF you could use for this. Okay, you could do like negative infinity or negative 100, negative 2.108, degrees of freedom of 20, and then that would give you that tail. And basically, this will be the same thing. So you just times this by 2. Okay, because it's a two-tailed. So as I said, you don't need to know this, but second bars is TCDF, negative 100, negative 2.108, degrees of freedom is 20. I already times it by 2, so that gives me my p-value,